All right, welcome. In this explainer, we're going to break down the fundamental chemistry you run into every single day. In everything from the food you eat to the soap you use. So let's just start with a simple question. Have you ever really thought about what's behind the sourness of a lemon, or that slippery feel of soap, or even just the taste of plain old table salt? Well, it turns out they are all connected. Okay, so here's what we're going to cover. First up, acids, the sour donors. Then we'll get into bases, the slippery givers. After that, we'll look at the neutralization reaction and, of course, meet the salts. And we'll wrap up with some other key chemical reactions. Let's get right into it. All right, let's kick things off with our first chemical character, the acid. This is the one that's responsible for that zesty tang in so much of our food. So what exactly is an acid? Well, scientifically speaking, it's any substance that produces these things called hydronium ions when you mix it with water. That's really the key to its whole identity. And it totally makes sense when you find out the word acid actually comes from the Latin word for sour. Okay, so how do you spot one? Well, you've got the sour taste, right? But they also conduct electricity in water and have a pH that's less than 7. But the real classic test is with litmus paper. And I've got a great little memory trick for you here. Think acid is like an alert. And what color is an alert? Red. So acids turn blue litmus paper red. Simple as that. Now this is super important. Not all acids are created equal. Not even close. They basically fall into two big families. On one hand, you have your organic acids. These are the weak ones found in nature, like citric acid in lemons or acetic acid in vinegar, the kind you eat all the time. But on the other hand, you've got mineral acids. These are the strong ones, like hydrochloric acid, and they're seriously powerful, corrosive industrial chemicals. A whole different ballgame. All right, on to our next character in this story, the base. And as you'll see, it is the chemical opposite of an acid in just about every way. Okay, so remember how acids release those hydronium ions? Well, bases are their perfect counterpart. They release something called hydroxyl ions in water. It's literally the other side of the chemical coin. Oh, and by the way, if a base can dissolve in water, we give it a special name, an alkali. You know that slippery, almost soapy feeling you get from things like bleach or soap itself? That's a classic sign of a base. And what's wild is that it's actually reacting with the oils on your skin to make a tiny little bit of soap right there. How cool is that? Besides that, they taste bitter, their pH is greater than 7, and the memory trick for the litmus test? Even easier. Just remember, base is blue. It turns red litmus paper blue. And just like acids, bases are absolutely everywhere. You've got the really strong ones like sodium hydroxide, the main ingredient in drain cleaners that just obliterates clogs. And then you have much milder ones like the magnesium hydroxide in milk of magnesia, which is literally designed to neutralize the acid in your stomach. So let's just put it all side by side. Taste, sour versus bitter. Touch, nothing specific versus slippery. Litmus test, blue to red versus red to blue. And the pH scale, below 7 versus above 7. I mean, they are perfect chemical opposites, right down the line. So, the big question is, what happens when these two total opposites finally meet? You might expect a big fight, right? But actually, something much more interesting happens. They perform what you could call a chemical marriage, and it's known as a neutralization reaction. And it works in this really elegant, simple way. First, you mix an acid and a base. Then those reactive ions we talked about, the hydronium and the hydroxyl ions, they immediately react. They basically cancel each other out. And what are you left with? Just two things, salt and water. That's it. And here's the absolute classic example of this. You take some really nasty hydrochloric acid and you mix it with some equally potent sodium hydroxide. And what do? You get sodium chloride, which is just regular table salt, and plain old water. It's amazing, right? Two dangerous things combined to make something you can put on your fries. Okay, so that brings us to the children of this chemical marriage, the salts. But here's a little twist. They aren't always perfectly neutral like you might expect. See, a salt's final pH really depends on how strong its parents were. It's like a chemical tug of war. If you have a strong acid and a strong base, they're evenly matched and you get a neutral salt, right around a pH of 7. But if you have a strong acid and a weak base, the acid parent wins out and you get an acidic salt. And if it's the other way around, a weak acid and a strong base, the base parent wins and you get a basic salt. The stronger parent always wins the pH battle. But neutralization is not the only trick these guys have up their sleeves. Oh no, acids and bases can have some other pretty important reactions. So let's check those out. Yeah, when they react with other stuff, you can get some pretty dramatic results. For instance, if you mix an acid with some metals, you'll actually produce flammable hydrogen gas. And think about that classic science fair volcano experiment, right? With the baking soda and vinegar. That's an acid reacting with a carbonate, and all that fizzing and bubbling, that's carbon dioxide gas being released. Okay, so let's circle back for a second and put what we just learned to the test. Here's the question. Why is ammonium chloride acidic? Well, it all goes back to its parents. It's made from a strong acid, hydrochloric acid, and a weak base, ammonium hydroxide. And just like we said, the strong acid parent wins that pH battle every time, overpowering the weak base and leaving the final salt acidic. And this right here is probably the most important safety takeaway from all of this. You absolutely have to understand the difference. You eat weak organic acids all the time, but you never even taste a mineral acid. They are highly corrosive, and knowing the difference is just critical. And that leaves us with one last really fascinating question to chew on. Think about it. Your own stomach uses strong hydrochloric acid to digest your food. So why don't you dissolve from the inside out? It's a great question, and the answer is a perfect example of this exact chemistry happening inside our own bodies.